Students, I am going to discuss about process capability in this session. Let me explain with the help of an example. The marks scored in mathematics by 7 students in a class are 75, 72, 78, 72, 80, 85 and 79. Find the mean and standard deviation of these marks. For finding the mean and standard deviation, we are using this formula. Process mean mu is given by sigma xi by n. It is equal to x1 plus x2 plus x3 plus xn by n. Process standard deviation sigma is given by square root of sigma xi minus mu whole square by n, which is equal to square root of x1 minus mu whole squared plus x2 minus mu whole squared plus x3 minus mu whole squared plus xn minus mu whole squared by n. Let us use this formula to find the mean of the mark of the 7 students. For finding the mean, we are adding all the marks of 7 students divided by 7. We get 77.29. For finding the standard deviation of these 7 mark, the first mark is 75. It is deviating from the mean of 77.29. So the deviation is found out by subtracting the mean with the 75 and you have to square the deviation. Similarly, second mark is 72. You find the deviation from the mean and we are squaring. So like that we are doing for all the 7 mark and we are adding all the 7 and divided by 7 and we are putting the whole square root. So that mark, that standard deviation value comes to 4.33 for this problem. So the mean of the 7 mark is arrived as 77.29 and the standard deviation of the 7 mark is 4.33. When the number of samples is very few, we can get the mean and standard deviation directly from this formula. When the number of sample is exceeding 50 or 100, then we have to use a table to minimize the calculation. Let us discuss how to find the mean and standard deviation using another practical problem. Now read this problem. An industry wants to produce shafts in mass quantities conforming to the dimensions shown in the figure. The industry has conducted a process capability study by producing 100 number of samples. The diameter of all the 100 samples have been measured and the measured values are tabulated in table 1. We have to calculate process B, process standard deviation. We have to find whether the process is centered or off-centered and what is the ppm defect of the process also we have to find out. So this is the second example. Now this is the blueprint drawing of the shaft. It is having a diameter of 12, minus 0, minus 0.06. Now the industry gets an opportunity to process this component in mass quantities. Before accepting this order, the industry wants to conduct a process capability study by running 100 samples. So the industry conducts the process capability study. It produces 100 samples as per the drawing and it has the industry has measured all the 100 sample. The diameter of the 100 samples have been measured, and these are the results of the inspection. Out of the 100 sample, one sample is measuring 11.94. 6 number of sample is measuring 11.95. 24 number of sample measures 11.96. So out of the 100 sample, what are the values of all these 100 samples is measured using a measuring instrument, and it's recorded. So if you count, if you sum up all these frequencies, it will come to 100. So most component, maximum number of component records a value of 11.97. So 38 number of components has a diameter of 11.97 measured by the measuring instrument. Let us find mean and standard deviation from this inspected results. For finding the mean and standard deviation, we will prepare a table. So the first row is the dimension, second row is the frequency. These two values have been taken from table number 1. The third row is the product of dimension frequency. So 11.94 and 1. When you find the product, it comes to 11.94. Similarly, 11.95 into 6, 71.7. So like that, we have to find the product of the first row and second row. That value you are going to add, you are going to enter in the third row. The third row, last column, is the total of all these values. So it comes to 1196.99. We are going to find the mean value with the help of this 1196.99. So the process mean is 1196.99 divided by 100. 100 is the sample size. So you get the mean as 11.97. Process standard deviation we have to find out again from the table. Now the 2 more rows are added. Okay, the third row is deviation from the mean value. So the dimension 11.94 is deviating from the mean of 11.97 by 0.3. The dimension 11.95 is deviating from the mean of 11.97 by 0.2. So like that, we are going to enter the deviation of the individual dimension from the mean value of 11.97 in the fourth row. Then the last row, fifth row, is frequency into square of deviation. So you have to multiply the frequency with the square of the 0.03. So 1 into 0.03 square, you are getting 0.0009. Like that, 6 into 0.02 square, you get 0.0024. So we are going to fill the last row in this way, and the total of the last row comes to 0.0111. The process standard deviation is found by entering square root of that last column value 0.0111 divided by the number of sample 100. You get the standard deviation of the 100 sample as 0.01. So we have got the answer for the first question. Process mean for the 100 sample is found as 11.97, and the process standard deviation is found as 0.01. Next thing, we have to find whether the process is centered or off-centered. What is centered or off-centered process? Now the 2 lines indicate the upper and lower specification limit. If the normal curve is centered between the two limits, it is called centered process. If the normal curve is not centered between the USL and LSL, it is called off-centered process. How to find whether it is centered or off-centered? Our example 2, whether it is centered or off-centered, how to find? So that rule you have to follow. If the process mean and drawing mean are same, it is centered process. If the process mean and the drawing mean are different, it is off-centered process. So what is the drawing mean for our example? So now the component has the upper value of 12, lower limit of 11.94. So upper specification limit is 12 and lower specification limit is 11.94. What is the mean of these two? What is the middle value? So middle of these two is 11.97. So this is the drawing mean. So for this example, the drawing mean is 11.97. What is the process mean we have arrived from the process capability study? Process mean we arrived as 11.97 from this table. Am I right? Yes. The process mean is 11.97. Process standard deviation is 0.01 for this example. So you look at this graph. The process mean is 11.97. The drawing mean is the middle value of USL and LSL. It is also 11.97. Both are identical, so the process center. If both are different, the drawing mean is 11.97. Process mean is not 11.97. Then it is off center. So we got the answer for the second question, whether the process centered or off center. So the process is centered. Okay, we got that. What is the next one? We have to find the ppm defect of the process. What is ppm defect? If you manufacture 1 million shaft, out of 1 million, how many will be rejected? So ppm is parts per million defect. For every 1 million pieces of shaft manufactured, how many number of work pieces will be rejected because it is not conforming to the given dimensions in the drawing. So this we can find by two ways. So the ppm defect can be found out using these statistical tables. So we have to find the area under the normal curve and we have to find the ppm defect. The second way is using a table that connects process capability ratio and the ppm defect. But the second option is only applicable for a centered processes. So let us see how to use the second method for finding the ppm defect for our example. So before we use the table that relates PCR and ppm defect, we have to find out the PCR for our problem. The process capability ratio PCR or CP is given by upper specification limit minus lower specification limit by 6 sigma. So for our example, the upper specification limit of the shaft is 12. The lower specification limit of the shaft is 11.94 divided by 6 times sigma. The sigma is arrived from the calculation as 0.01. So if you find out the value of PCR, it comes to 1. So once you know the value of PCR, you can refer to the table. So this table relates CP value or PCR value with the ppm defect. So we got the value of PCR as 1 for our example. So what is the ppm defect? 2700. So if you manufacture 1 million shaft, 2700 of them is likely to fall out of the two limits. So the ppm defect for this example is 2700 since it is having a PCR value of 1. So this comparison between the PCR and the ppm DFAT is applicable only for a centered process. Now we have to refer to two-sided specification for this problem. What is two-sided specification? What is one-sided specification? When the shaft, the dimension has to be limited on both the sides, upper side and lower side, it is called two-sided specification. So if you look at the drawing, the shaft has to be manufactured between upper limit of 12, lower limit of 11.94. So in both direction, the dimension has to be limited to within this range. So it is a two-sided specification. So we have to follow the second column, two-sided specification, for finding the ppm DFAT. What is one-sided specification? In some cases, you will be giving only the one limit. If you want to give a specification of a strength of a beam, the minimum strength of a beam will be given. So the maximum strength can be anything. So it is called one-sided specification. The strength of a beam is given and only one minimum side only is given. The maximum side is not given. So it is coming under one-sided specification. So if you want to find the ppm DFAT for such one-sided specification, you have to refer to the first column. Now we have to answer the third question. So what is the ppm DFAT of the process? So from this we got the answer as 2700 parts per million as the ppm DFAT. So since the process centered, we are able to refer to this table that connects CP and process fallout in parts per million. So PCR value recommended is given in this table. Minimum recommended value of PCR is given in this table. Just refer to the table. Existing process for two-sided specification 1.33. For one-sided specification 1.25. New processes 1.5, 1.45. Safety, strength or critical parameter existing process 1.5. One-sided specification 1.45. And safety, strength or critical parameter new process 1.67 and one-sided specification 1.6. So these are the recommended minimum value of PCR for existing processes and new processes.